Right, so it's the next day from day 6, and we've made a bit of a Git faux pas in as much as we've accidentally git clean -f and removed the source file. So we're back to not having our source for the answer to part 1 of day 6, which means we need to rewrite it. It's kind of annoying, but that happens. So I thought instead of just trying to rewrite it exactly how we did it before, I thought it'd be fun to try and render out this maze as console outputs and then have it update sort of every frame so we can see where this cursor's moving just for fun. So we're going to try and implement that. I found online this bit of code here, which I quite like. These two special magic characters where you can manipulate the console to clear previously written lines. I wanted to give that a go just for fun and see if we can make it look cool. So I've got my blank file and I'm going to paste these 2 lines here just so we can have a go with it. And now we need to rewrite our previous implementation. So let's give that a go. Right, let's do a bit of a voiceover here and save you watching me type out code in real time. So we're going to bash together a vector class. I'm sure there's libraries out there that have vector classes that we could use, but it's so simple what we want out of this one that we just bashing one together. I might have looked into Pygame. I know they've got a vector class, and that might have been a better approach. But in any case, we have a new class for our maze, and then we're going to store up the obstructions and the guard's position and direction. And then we also want a parse function, which is going to take that string input and convert it into our data. And for that, we need an enum. So we're going to use this class enum structure so that we can create a map, a dictionary that will map the character that's incoming in the input to the enumerated type of what's at that point, of which we're going to have either the guard, the obstruction, or just an empty cell. Maybe if you're eagle-eyed, you'll notice I've made an error there in that map and I've used obstruction where I meant to use guard, but I'm going to see that I end up having to debug that in a minute. So yeah, grab the character from the map, and if it's a guard, then we set the guard up. Else, if it's an empty cell, we can just ignore it. Else, if it's an obstruction, we just append that to the list of obstructions. And that's all we need to parse in the data. So let's set up a test case and assert that our result is what we expect. Of course, we haven't actually written the traversal function yet, but this is just the setup, kind of like unit testing style. Write the test case and then fill in the implementation. So to traverse this map, we're going to need to create a path, which is a list of all the positions we've visited after we have some tea. So create a path, which is a list of all the positions we visited, and keep going until the guard is at a wall facing the wall. So we need to create that function, is guard at exit, which is he on one of the edges of the map, and is he facing to the outside of the map. Obviously, to do that, we need to actually get the map dimensions. So we parse that out in the parse function as well. So if the guard is at any of the edges and facing towards the edge, then they are making an exit. Let's code up that. So then the decide position is the position plus the direction, and of course we need an add function in our vector for that. And then we need to see if there's an obstruction at that desired position. If there is, then we need to rotate the guard clockwise, I believe was the instruction. So we need a function to rotate the direction given an input direction. Otherwise, we can add that new position to the path and set the guard's position to that new position. And by the end of it, we can take the path that we built and we convert it to a set, which will give us all of the distinct entries in the list, which is what the output wanted, and then use the len function to see how many entries were in that set. So that will give us the distinct positions. You see how I had a bit of a debug session here. I couldn't quite work out why my maze was saying it had no attribute of guard position, even though it was in the constructor. But the problem was that I didn't actually construct the field to have any value. So for whatever reason, it wasn't actually in that structure. So I had to assign it to something for it to be existing, which I didn't really realize was a feature of Python, but hey ho. And then what was the next thing we encountered? Oh, I think it was just an infinite loop. So this is me trying to debug what was going on. We see that the guard position and direction wasn't actually parsed. They were at the origin. So now I'm just realizing that my character map didn't have the right actor names for the guard type. It's flagged as obstruction and not guard. So eventually we'll realize that. But thank God for VS Code and its debug capabilities. I used to have to do this with the Python MPDB syntax, and then it's all like inside of the shell. And that sort of debugging is quite handy that it exists and you can do it, but it's so much easier to debug with a visual IDE. So we got an error with the hash function as well, but eventually, after all said and done, I think we're happy with the implementation and we got our final answer. And this time we're actually going to commit it to Git so we don't lose the file again. There we go. All right, okay, so we're back and we had a bit of an interlude. I ended up writing like an extra bit for printing out the current map. As you can see here, I've got like the map as it appears in the instructions. So I've got the print function here, but I've also added this return console return function where the cursor gets taken back to the start and then we can print again over the top of the existing thing. I'll show you what that looks like. So it's a bit shimmery, a bit flickery, so I'm not super blown away by the animation. I think maybe Pygame or some other framework where we actually have a proper window and we can blit to that window might be a more fun approach, so I might look into that another day. But for now, we've still got part 2 to tackle. So I'm going to have a quick look at that now and see where we need to go for part 2. So part 2 is all about the guard's patrol route, trying to work out what we can do to get him stuck in a loop to make the lab safe to search. So we'd like to know all of the possible positions for an obstruction that would get the guard to get stuck in a loop. So there's 6 different positions where a new obstruction would cause it. So in this sample, there's 6 particular things we can add. So basically we need to add a is guard stuck in a loop function to our original traversal, and then we need to go through every single point on the map that doesn't already have an obstruction, and if adding one and rerunning the traversal gets him stuck in a loop, then we consider that a loop. And we're trying to work out how many different positions could you choose for the obstruction. Okay, so just count up, go through every single possible position, add an obstruction, and for any one where the guard ends up stuck in a loop, add it to the sum, and that's our answer. Okay, let's code up that. So first things first, we need the is stuck in a loop, which is probably would have been a good practice to do this anyway. I was worried about this while loop having an infinite loop in there. So now we get to actually code up the answer to that. So in order to do that, all we need to do is see if the desired position is already in the path, and also whether the guard direction is the same as it was before, so we need to store path directions as well, so that we know that he's actually facing in the same direction as he was before, because it could just be a crossroads. Right, so let's add the guard direction to that path directions, and then every time we change the path, we'll also add the path direction on. So here, direction, path directions, and then so this steps I added just for the animation thing, so we'll ignore that for a minute. So here we'll do the check, I guess. So for every position in the current path, put the point and the path index. Oh wait, no, that seems fine. Let's just run it on the shell, I think. Oh, it's running so slowly. Alright, and we're back. So after a bit of debugging of why it was so slow, all I've done is I've converted this list to a set, so that when it's checking for obstructions, it's looking in that set instead of searching a list. I'm surprised the difference that makes, but apparently that makes quite a big difference. I don't think I made any other changes. So yeah, it's now gotten through and we've gotten an answer. So just finish now and let's find out whether we actually got the right answer, which we have. So there we go. That's the end of part 2. That was a little bit more tricky than the previous one. I started thinking about whether we should go down the multi-threaded route, and then I was considering trying to upgrade to Python 13, so version 3.13, the next version up, because of this global interpreter lock improvement that they've made, whereby you can disable this and get a lot more performance out of Python. But in the end, I thought by the time I had rewritten it with that, I thought it would have actually finished. But actually, having found this optimization here, that did the job. It was suitably quick, and I didn't need to go down the multi-threading route. But yeah, I think multi-threading in Python is a bit of a pain in the butt, and not really much performance to be gained with multi-threading because of the global interpreter lock problem. But with that new version, maybe there's some mileage there. But I might try that another time. Next time we hit a puzzle where it needs some extra performance, I might give that a go. But in any case, there we go. Finally managed to get to the bottom of day 6. So signing off.